So we're going to continue our discussion in section 7.1, which deals with finding critical values that correspond to a certain confidence level. And so previously we discussed a critical value of z, called z sub alpha over 2, is the borderline separating sample statistics that are likely to occur from those that are unlikely to occur. A critical value is calculated based off of a given confidence level and a corresponding value of alpha. The higher your confidence level is, the larger your critical value will be, which will create a wider interval. Okay, so we're going to calculate a couple of these. Find the critical values that correspond to a 95% confidence level. And so I'm going to go ahead and draw a normal distribution. And so our confidence level, CL, is 95%, and as a decimal is 0.95. Alpha is always 1 minus 0.95, so 0.05. And then you take alpha and divide it by 2, so 0.025, right? So what this is saying, I'm going to draw my critical values. I have a negative 1 over here and a positive 1 over here, right? And so alpha over 2 we found was 0.025, 0.025, right? So our confidence level goes in the middle, so 0.95. And what is left over? If we have 95% of the graph in the middle here, remember the total area under the curve is 1, right? So if 95% is here, left over is 5%. Well, you take that 5% and divide it by 2. And so 5% divided by 2 is 2.5% that goes here, and 2.5% goes here, right? 0.025 is a decimal, 0.025 is a decimal. Notice if you add up the area here, plus the area here, plus the area here, the total area under the curve is still 1, right? So to find these critical values, they're actually the same number, one's just negative, but I'm going to go ahead and calculate the negative one. So it's inverse norm, right? To calculate z-scores, use inverse norm. The area to the left of this critical value here, well, what's the left of it? That's this region right here. So 0.025, the area to the left. The mean is 0 because we're dealing with the standard normal distribution. And the standard deviation is 1, right? So you go to your calculator, press second vars to open up the distribution menu. The very third option is inverse norm. Area to the left is 0.025. Go ahead and clear that out, and I'll just retype it, 0.025. Press enter, 0, 1, enter, press enter, enter again, and you end up with negative 1.9599, and so on, right? To calculate that positive one, it's inverse norm. The area to the left of this z-score, well, what's the area to the left? Well, it consists of two regions, this region here and this region here. So the area to the left is 0.95 plus 0.025, right? You have to add up this probability here, or this area, plus this area. That's going to be the area to the left of this z-score. So if we add those up, we end up with 0.97501. Clear it out, press second vars, go down to the third option, the area to the left, and then the mean and standard deviation stays the same. And you get the positive one here. So the critical values that correspond to a confidence level of 95% is plus or minus 1.96. Okay, we're going to typically just look at the positive number here. Okay, so find the critical values that correspond to a 99% confidence level, right? Well, a 99% confidence level Your confidence level goes at the center of the graph, so 99% or 0.99 is a decimal. Well, alpha is always 1 minus the confidence level, so 0.01. Right? But you have to take alpha and divide it by 2. So the 0.005 and 0.005 goes on the tail ends of the graphs, right? You have 99% in the middle, 1% left over. So you take that 1% and divide by 2, 0.5% here, 0.5% here. And so we need to calculate these critical values here. So alpha over 2 is 0.05. Right? And this one, of course, is going to be negative. So use inverse norm. The area to the left, you can calculate the negative one here. The area to the left of this, well, the area to the left of is this 0.005. Your mean, your standard deviation. So you go into your calculator, you press second, vars, go down to the third option, press enter, and then you type in 0.005. And you end up with negative 2.575829 and so on, right? But we would round to 3 decimal places. So the critical value here that corresponds to a 99% confidence level is 2.576, right? The z values that correspond to the confidence level is 2.576. So notice here, our confidence level went from 95% to 99%. We want to be more confident here because the confidence level has increased. Notice the corresponding z-score or critical value has also increased, right? Which creates wider intervals. Okay, so this chart here deals with the most common critical values that you're going to use. These are the ones you're going to use most of the time, and you will have these on the test. You will not have to memorize them. So if your confidence level is given in the problem, this is the critical value that you're going to use to create a confidence interval. So if you have a 90% confidence level, our critical value is 1.645. If our confidence level is 95%, our critical value is 1.60. And if our confidence level is 99%, we end up with, sorry, I interchanged these, 2.576. 2.576. So notice as our confidence level goes up, right, as it gets larger, so do our critical values. Okay. So note, as the confidence level increases, so does the z-score, which then creates a wider interval. Okay. So next, we're going to look at margin of error. When data from a simple random sample are used to estimate a population parameter, the margin of error, which we use E to denote that, the margin of error, use uppercase E, is the maximum likely difference between the observed sample value and the true value of the population parameter, and is also called the maximum error of the estimate. Okay, when we're calculating for proportions, the margin of error is calculated by taking the critical value z alpha over 2. Remember, this critical value corresponds to your confidence level, and you can get it from this chart here. So if the problem says you have a 95% confidence level, then the critical value you would use is 1.96, right? And so you take that critical value and you multiply by the square root of p hat times q hat divided by n. Okay, so this is the formula you need to calculate your margin of error. Okay, when constructing a confidence interval for the population proportion, you can write the interval in three different ways, right? First, you can write it p hat plus or minus e. Next, you can write it p hat minus e, p hat plus e. And then lastly, you can say your proportion p is somewhere in between p hat minus e, p hat plus e. Okay. So if we go back to the very beginning, just to kind of show you an idea. Very beginning, we said that we collected a sample of 100 students, found that 30% of those students work full-time, right? 30% is a good single value to help us estimate the true proportion of all students at LSUE who work full-time. So the single best value we have is always our sample proportion, which is 0.30 in that case, right, from those 100 students, right? So let's say we calculated a margin of error. I'm just making this up. We calculated a margin of error, and we found that the maximum difference between the true proportion of all LSUE students who work full-time and the sample is 0.10, right? To create our confidence interval, you could say, okay, p hat plus or minus your margin of error, which is 0.10, right? That's this way to write it. Or you could say, I'm going to write it as an interval, and I'm going to take 0.3 and add 0.1. That's going to give me 0.4. That's going to be my upper limit. And then I'm going to take 0.3 and subtract off 0.1. It's going to give me 0.20. And so this would be my lower limit for my interval and my upper limit, right? And so my lower limit would be 0.20. My upper would be 0.40. And so what this is saying is that we're getting a little more confidence in our estimate. Just saying 0.3 is okay, but saying that the true proportion of all LSUE students who work full-time is somewhere between 20% and 40%, that's a much better estimate, okay? And then the last way we can write it is like this, using an inequality. The proportion for all LSUE students, P, is somewhere between 0.20 and 0.40. Right, and this is just kind of an example showing you the three different ways you can write your confidence interval, right? Interpretation of the confidence interval, okay? We are C% confident, so we are 95% confident or 90% confident that the true proportion of the population is between p hat minus e and p hat plus e. If we repeat this survey a large number of times, if we repeat this survey a large number of times, we expect that C% of the times we will get a value between p hat minus e and p hat plus e. So these are kind of two different ways to interpret the interval. And that's it for this video. We're going to continue our discussion and look at examples on actually creating the confidence intervals in the next part of this video.